Now, the indicated work or indicated power can only be calculated if we have the PV diagram at hand. Now, to get the PV diagram, of course, we'll have to take out the pressure data from the cylinder. So that cannot be done in practical engines because we'll have to make a permanent modification, insert a pressure probe or the pressure sensor inside the cylinder to get this pressure data out. So that is practically not possible in practical engines. Only that can be done in test engines in laboratories. Therefore, the indicated power or indicated work per cycle is something that we can't calculate or measure in most real engines. Accordingly, what we measure from real engines is the brake torque or the brake power. So usually we measure the brake torque and then we can calculate brake power. So the meaning of the word brake torque, perhaps you are familiar with. That is, what we try to do here is we are trying to apply a certain resistance on the crankshaft of an engine. And we are going to observe the performance of engine under different resistance. So we can change the resistance and observe how the engine behaves under different resistive forces. So the brake torque or the brake power can be measured using a specific device called engine dynamometer, or in shortened forms, it is known as engine dyno. And there are several different types of dynamometers that can be used for engine testing. But the most common type that we frequently find in modern day experimentation is the eddy current engine dyno. Eddy current engine dyno. So in our test rig in the applied thermodynamics laboratory, what we have there in this engine is an eddy current dynamometer. The operation of a eddy current dynamometer is quite simple, which is an electromagnetic device where a metal rotor is connected to the engine crankshaft directly, and it is sent through an electromagnet. So the electromagnetic strength can be controlled by controlling the current flow or current supply to this electromagnet. So the eddy currents created here applies a certain resistive force against the rotation of the rotor or the rotation of the crankshaft in this case. Accordingly, we can apply certain kind of a brake on the crankshaft, and that is, in fact, the resistance against the rotation of the crankshaft. So we can apply a load on the crankshaft by sending certain current through this field coil, and accordingly, we can measure the torque applied on it and observe the engine performance accordingly. So the torque measuring system, you can see here, there is a shaft coming out from the eddy current dynamometer, and there is a load cell connected to it through a cable. And then whenever there's a certain resistance applied on it, this shaft tends to move upwards or rotate, and that rotation is held up using this connection over here through the load cell. So the load cell reading gives us the force, and the distance is, in this case, to the center of rotation is B. Therefore, the torque on this can be estimated in terms of multiplication of F and B. So that is the torque applied on the engine, that is called the brake torque. Now, if you know the speed of rotation of the engine, and if you can measure the brake torque using eddy current dynamometer, then the brake power can easily be calculated. So the brake power is measured or estimated the way that I just explained. Using eddy current dynamometer, what we measure is the useful torque or useful power that we can take out from the crankshaft of an engine. And earlier we looked at the indicated power and indicated work per cycle. And the difference between these two quantities is more or less the friction. So the friction forces makes the difference between the brake power and the indicated power. So the indicated power is something what happens inside the cylinder thermodynamically. And when it comes to transmitting that power into crankshaft, then there are a lot of frictional elements. So accordingly, the relationship between the indicated power and the brake power is, of course, when you add the frictional effects on the brake power, you get the indicated power. And the mechanical efficiency is defined as the ratio between brake power and the indicated power. Brake power and the indicated power, that indicates that the how much of frictional effects are there. So if the mechanical efficiency is larger, the frictional losses will be smaller, and vice versa. So these are some of the values of mechanical efficiencies of an engine, just for you to get a sensible understanding. Under full throttle conditions, a spark ignition engine may observe something like 90% of mechanical efficiency. And if the engine is idle conditions, of course, we are not taking anything useful out of the engine. So the mechanical efficiency could drop down to 0. So it can vary between these two limits. And on average basis, it can be around 80%, 75% in most of the operating conditions. Brake power or indicated power that we computed earlier, highly dependent on the size of the engine. That is, if the displaced volume is larger, then you could produce large amount of power. Or if it is smaller, then the power production will be smaller. So when it comes to comparing different engines of different sizes, in fact, the direct comparison between the brake power or indicated power is quite misleading. So we need a size independent parameter in order to compare the performance of engines of different size. So the common parameter that we use to compare different engines, performance of different engines, is the mean effective pressure. So the mean effective pressure normalizes the work done by an engine to the displaced volume of it. In simple speaking, it is defined as net work of the engine divided by the displaced volume, that is maximum volume to minimum volume, so that we can find an average quantity which is independent of the size of the engine. So that is something that we could frequently use to compare engines of different sizes. Now, the mean effective pressure, again, of course, by definition, it is work per cycle divided by the displaced volume. The work per cycle is something that we cannot measure in practical engines, because we need a pressure probe inserted into the engine to work out the indicated work per cycle. And at the same time, the engines run at very large speeds, like 1000 RPM and so forth. Accordingly, for example, if it is a 4-stroke engine, runs at 1000 revolutions a minute, will create 500 cycles per minute. So the time duration per work per cycle is very short. Accordingly, the parameter that we would like to use to discuss the operations are not the work per cycle, but the power. So we can convert this work per cycle into power by considering the formula that we looked at earlier. That is, power equals work per cycle into N over NR, where N is in revolutions a second, and NR, depending upon whether it is 4-stroke or 2-stroke, it will be either 1 or 2. So accordingly, mean effective pressure is P NR VD over N. N is in revolutions a second, and NR is 1 for 2-stroke and 2 for 4-stroke engines. And when it comes to calculation of mean effective pressure, usually we represent it in kilopascals or bar. If it is, if you want to represent it in kilopascals, then you'll have to use the right units in substituting values for power, displacement, and the speed. So mean effective pressure is directly proportional to the power of the engine for a particular engine at a given speed. And at the same time, mean effective pressure is directly proportional to the torque of an engine per given displacement or the displaced volume. So if you use brake power or the brake torque to calculate mean effective pressure, that mean effective pressure will be brake mean effective pressure. If you use indicated power, indicated torque to calculate mean effective pressure, that will be indicated mean effective pressure. So indicated mean effective pressure will be equal to brake mean effective pressure plus the friction mean effective pressure. This table gives us an indication about the real values of brake mean effective pressures in kilopascals. Now, if you look at a naturally aspirated spark ignition engine at maximum torque, where the speed is around 3000 RPM, the brake mean effective pressure in the range of 850 to 1050 kilopascals. And at the same time, at the maximum rated power, it can be 10 to 15% lower than that. So that indicates that brake mean effective pressure is highly correlated with the speed of the engine, because the speed at which the maximum torque is obtained in practical engines is somewhat lower than the speed of which you could get the maximum power out. So that we can discuss later, the reasons for that. And if it is a turbocharged engine, brake mean effective pressure could be increased to up to about 1700 at maximum torque, and maximum power, it could be around 900 to 1400 kilopascals. So in all these diagrams, you can see the brake mean effective pressure changes with the speed. And if it is a diesel engine, of course, compared to petrol engines, the brake mean effective pressure of diesel engines are slightly lower. You can see at maximum torque, naturally aspirated 4-stroke diesel engine, it's in the range of 700 to 900 kilopascals. Whereas if it is a spark ignition engine, it will be around 850 to 1050 kilopascals. And so those the reasons for those we can discuss later in detail. But for the moment, as a simplified answer, what I could give is the reason is the diesel engines are heavier and develop a lot of high pressure inside the combustion chamber during combustion and the expansion. Accordingly, the frictional losses and the inertia losses, the engines need to be made heavier and stronger. Accordingly, the frictional losses and the inertia losses are high. Therefore, the brake mean effective pressure is comparatively less in diesel engines than the spark ignition engines. But anyway, there are many other parameters which affects on these. We could discuss those in detail as we go. Now, this graph shows us the effect of the parameters that we just discussed on the speed. Now, you can see the brake mean effective pressure peaks somewhere here around 2000 to 2500 or 2200 RPM in this particular engine. And then after that, it starts dropping down. And indicated mean effective pressure also peaks around nearly 3000 RPM, and then again starts dropping down with the speed. And one reason for the reduction of brake mean effective pressure with the speed, after some speed, of course, initially it increases, but after some speed, it starts dropping down. One reason you can simply see here, the friction losses increases with the speed, because viscous friction is directly proportional to the velocity, the speed of the rubbing components. Accordingly, the frictional losses getting higher and higher with the high speeds, and the brake mean effective pressure will have to drop. And at the same time, with the increase of speed, you can see the indicated mean effective pressure also comes down. That is mostly because the volumetric efficiency of an engine reduces with the after certain speed. After certain speeds, volumetric efficiency starts dropping down just because of the the flow losses. There will be a lot of turbulence in the intake system, and the high-speed flow will increase the frictional losses on the wall areas. Accordingly, the volumetric efficiency it drops down after certain speed. Accordingly, indicated mean effective pressure drops. So as a result of dropping down the volumetric efficiency as well as increasing the frictional losses, obviously the brake mean effective pressure drops down. And the same thing happens for brake power. So the brake power peaks somewhere here and starts dropping off, and indicated power also will continue to increase, but the rate getting smaller because of this loss of volumetric efficiency. Now, if you move on to air-fuel ratio, as you all know, air-fuel ratio is defined as the ratio between air and fuel. And this MA is air induced per cycle, and MF is fuel introduced per cycle. As I said earlier, per cycle measurements are practically not very possible in real practical engines. Accordingly, what we could measure is the flow rates, air flow rate and fuel flow rate. Now, in modern engines, of course, there is a sensor, airflow sensor fitted in the intake system to measure airflow, and fuel flow sensor is fixed in the fuel line to measure the fuel flow. So these quantities are readily available in the engine control system. Now, spark ignition engines, as I indicated earlier, we need to operate around the stoichiometric air-fuel ratio to get the best outcome. But in certain situations, we prefer to have rich mixtures, and certain situations we prefer to have lean mixtures. Now, as I mentioned at one of the previous lectures, at the cold start, we prefer to have a rich mixture in the sense air-fuel mixture with more fuel in it than the stoichiometric, so that we can initiate the combustion easily. And at the same time, as far as the emissions are concerned, unwanted gases going out of the tailpipe is concerned, then it is always good to burn lean mixtures, slightly lean mixtures. So there is a compromise. So depending upon the requirements, we can slightly change this air-fuel ratio dynamically, but not a lot, but maybe in the range of 12 to 18, where the stoichiometric air-fuel ratio it's around 14.7. But on the other hand, in diesels, of course, we do not throttle diesel engines. So we let the engine to produce power according to the amount of fuel that we inject. So we take full amount of air in, and depending upon the power requirement, we decide how much of fuel to be injected. In that case, compression ignition engines operate in a wide range of air-fuel ratios, maybe from 18 to 70. The equivalence ratio is something that we prefer to use instead of air-fuel ratio in normal operating jargons, which is in fact a quantity which is normalized to the stoichiometric air-fuel ratio. Usually denoted by phi, air-fuel ratio stoichiometric divided by actual air-fuel ratio gives you the equivalence ratio. On the other hand, fuel air ratio divided by the stoichiometric fuel air ratio gives you the equivalence ratio. So as you can see here, if a mixture is rich in fuel, so more fuel than stoichiometric air-fuel ratio, then it is a rich mixture, and that means equivalence ratio is greater than 1. So if more fuel, equivalence ratio is greater than 1, and that means it is a rich mixture. But if you have less fuel than the stoichiometric air-fuel ratio, so this quantity is larger than this quantity, therefore phi will be less than 1, so that is a lean mixture. And in practical engine jargons, sometimes instead of equivalence ratio, we use something called lambda. lambda is 1 upon equivalence ratio. Lambda is 1 upon equivalence ratio. So at stoichiometry, lambda equals phi equals 1. So for rich mixtures, lambda is less than 1. For lean mixtures, lambda is greater than 1. I think you have heard of this term lambda as far as the engines are concerned, because there is a popularly known sensor called lambda sensor in engines. So the role of the lambda sensor is just to monitor whether there any excess oxygen going out of this tailpipe from the exhaust system. So the lambda sensor is usually connected to modern engines to monitor whether there is any oxygen going out of the system. So oxygen going out of the system is means that the mixture is not stoichiometric. Complete combustion is not taking place. So according to this, if you want to operate the engine at a stoichiometric airflow ratio, the feedback that you get from the lambda sensor is used to make decisions about adjusting the amount of fuel to be mixed with air in the intake system. So that is how the airflow ratio is practically calculated in computer control engines. You measure air and fuel and mix them. At the exhaust side, you measure whether there is any oxygen going out of the system and make the corrections of these initial calculations based on the feedback signal.